Hello everyone, it's time for another class and we'll be dealing with the models of atom in this particular class and I expect you to pay rapt attention so you obtain the best. Please pay attention as I share my screen and also there might be some background noise but please pay capital attention because I'll try to be as loud as possible. I'm going to share my screen right now and let's dive in. Here we go, models of atoms. And I'm going to start with the fact that I want to first of all speak about the Thomson model. And when it comes to the Thomson model, the Thomson model, or let me say in the Thomson model, Thomson proposed the atom as a homogeneous sphere of positive charge inside of which are embedded negatively charged electrons. So the idea here by Thomson is that the atom is a positively charged sphere that has electrons inside. So let me make that drawing again. Positively charged sphere with electrons within it. Electrons embedded. It's good to mention that E also determined, that is Thomson, he also determined the ratio of the charge to mass. That is, people do that as a electron per mass. So the charge to mass of electrons. And found that ratio to be identical for all cathode ray particles or cathode ray particles. Irrespective of the kind of gas in the tube or the metal the electrons are made of. So you see that it determined the ratio of charge to mass of electrons and found that ratio identical for all cathode ray particles, irrespective of the kind of gas in the tube or the metal the electrons are made of. So please take note of that solid point. That's a summary of the Thomson model. We'll have a deep dive now into another model called the Rutherford. The Rutherford model. He proposed a planetary model of atoms. He suggested that the atom consists of positively charged core called a nucleus, where most of its mass that is the mass of the atom are concentrated. And has negatively charged electrons circle in orbit, much as planets move around the sun. So the idea of this model is that it says, okay, diagrammatically, there is a nucleus at the center which has protons, positive charges inside. This guy is called the consists of positive charge core, yeah, protons, and then this core that contains those protons, and I'm going to put the neutrons as square, and neutrons, that core that contains protons and neutrons is called nucleus. Why there are other circles around that, and on those circles like orbits, we have electrons. So I'm going to repeat it. We have nucleus containing protons and neutrons. So protons, the nucleus contains protons and neutrons. And around that nucleus, we have orbits cycling round. And those orbits contain things called electrons. So that is the idea of Rutherford. So those orbits are like the orbit of the planet around the sun. That's the simple idea. We now call something the limitation of Rutherford model. Limitation of Rutherford model. Number one, it predicts that light of a continuous range of frequencies will be emitted, whereas experiments show line spectra instead of continuous spectra. It also predicts that atoms are unstable. And the meaning of that is that electrons quickly spiral into the nucleus. But we know that atoms in general are stable. Since the matter around us is stable. So Rutherford model is trying to say atoms are unstable because electrons quickly spiral. But that contradicts what we know. What do we know? That atoms are stable because matter around us is stable. That's the idea. And the same thing, it also predicts that light of continuous range of frequency will be emitted, whereas experiments show that line spectra instead of continuous spectra. So Rutherford model predicts line spectra, but experiment shows continuous spectra. So that's the idea here. Now move forward to the another model called the Bohr's model. And what is the Bohr model about? I'm drawing it first before I write about it. Let me move some things. So the Bohr model has to do with, I'm going to draw this first before I explain. So he suggested, so this is like the diagram we have. He suggested a model of hydrogen atom, Bohr model. Suggested a model of hydrogen atom in which the electron moves around the nucleus in a certain specific circular orbit called the energy level. And that the centrifugal force due to this motion counterbalances a electrostatic attraction between, oh, let me, between the electron and the nucleus. I will advise you, go and read this note. You should, by now, you should be a student that goes back to your notes, reads, drags out the important points. The electron moves around the nucleus in certain specific circular orbit called energy level, and that the centrifugal force due to motion counterbalances the electrostatic attraction between the electron and the nucleus. Now, in the diagram, this is the nucleus. These things are the orbits, and of course, this guy, I can move it from there. Okay, let me move. Okay, let me just erase it then. Since I'm not. So this guy, I was representing it with electron before, but I can put some here, put some here, put some here. So I'm calling this the electron for hydrogen. So that's the electron. You will understand why I put Z in front of it. So we're talking about the hydrogen atoms. And these orbits, they are representing energy levels. So that's what that first definition is saying. Energy levels. You see one that is n equal to 1. That's energy level 1. Next one, n equal to 2. Like that. So electrons are on them. Of course, they are orbits. Then the stuff at the center is the nucleus. Then you see this movement like this. Let me make this proper. You have it this way. Let it be a circle. You see this movement when an electron drops from a higher energy level, like let's say like 3 to 2. It requires energy to be released, right? When energy is released like that, that energy is Planck's constant times frequency. So we'll go there. We'll get there to that explanation. But in the first point now, we said the electron moves around the nucleus in certain specific circular orbit called energy level that they such that the centrifugal force due to this motion counterbalances the electrostatic force between the electron and the nucleus. Now, centrifugal force that keeps it orbit. You know, centrifugal force is what keeps it moving in orbit. It must balance the force of attraction between the nucleus and an electron. Why? Because the nucleus is considered to be positively charged, while the electron is negatively charged. So you get the idea. So yeah, let me correct something. These stuffs that exist on the orbit are called electrons. Why that thing that I put here before was a symbol that the nucleus is positively charged. So let me erase this. So if the nucleus is positively charged and electrons are negatively charged, there's definitely a force of attraction between the nucleus and the electrons. But this first point is saying that, oh, we've established that, oh, the electrons move in orbit. But the centrifugal force must balance, centrifugal force must balance the electrostatic force of attraction between the electron and nucleus. Let's now continue making a point there. And that point is saying that the electrons can move without losing or radiating energy in such orbits. The electrons can move without losing or radiating energy in such orbit. The electrons can move without losing or radiating energy in the orbit. The idea is that, if they stay in their orbit, if they keep moving now on this particular orbit, you can move from here to here on this orbit, they don't need to radiate or lose energy. But once they move from a particular orbit to a lower orbit, let me put that in red. Once they move there from here now to a lower orbit, now that's a different scenario. Let's continue the statement we're making. Can move without losing energy in such orbits. That is, so those orbits are called, they are called possible orbit stationary states. And we must identify that the higher the energy of the electron, the farther its orbits from the nucleus. The higher the energy of the electron, the farther its orbit from the nucleus. Straightforward. The next point we're making here is that the energy of an electron in an atom cannot vary continuously to a limited number. Okay, let me put this grammar well. The energy of the electron in an atom cannot vary continuously. Then let me put full stop. It has a limited number of discrete values called quanta. So we say the energy of the electron is quantized, like it has a specific quantity. So the idea here is that the energy can exist in levels like n equal to specific energy levels, like n equal to 1, n equal to 2, n equal to 3, like that. So you don't have things like 1.5, no. It only exists in quantized, discrete values like this. So you don't have things like this. N cannot be equal to other values like that are not discrete, that are not quantized. So the energy here, limited discrete values in quanta, we say the energy of the electron is quantized. So keep that in mind. Then it was also under this second point that we have postulate. He postulated, he postulated, this is Bohr model now. He postulated that electrons in an atom cannot lose energy continuously, but must do so in quantum jumps. So keep that in mind. Now, he said, postulated also that light is emitted only when an electron jumps from, and we say emitted, we say released or released. That's what I was saying before. And when we say light is released, we are saying like light energy is released when electron jumps from higher energy level to lower energy level. That was what I was saying when I was in the diagram, where I said if you have a case where an electron jumps from here to here, we have energy, there's energy release as this. So let's put that in perspective now. We say when such jump occurs, a single photon of light, it's a photon of light, a single photon of light would be emitted whose energy is given by change in energy equal to HF. A change in energy means energy of the final minus the energy of the initial state equal to HF. And what is the meaning of HF? Let's explain all those terminologies. EF now is energy of upper state yeah, let's use upper and lower. No, let's use final and initial. Yeah. Energy of final state, energy of initial, yeah, let's use upper and lower. Yeah, energy of upper state, let's just do upper and lower. Energy of upper state, there's energy of lower. So let's use U and L. Sorry about that. U and L. energy of lower state. And in this case, H is something called Planck's constant, and is given by 6.67 times 10 raised per minus 34 joule seconds, while F is frequency of emitted light. Sorry, my screen must have gone off at this point. Let me quickly fix that. Frequency of emitted light. Yeah, so we have established that Bohr was able to account for the appearance line spectrum rather than continuous spectrum. So it is Bohr that was able to account for line spectrum rather than continuous spectrum. Yeah, and that line spectrum is more like the energy level thing, where we have, for now, energy level in form of lines. Let me draw straight lines. And the lines go on like that. Where we have n equal to 1, n equal to 2, and it keeps going like that. So again, we must mention that an electron absorbs energy when it transfers to higher energy level. I will call this excitation. So when electron moves from, e.g., when it moves from n equal to 1 to n equal to 2, or n equal to 2 to n equal to 3, or say from n equal to 1 to n equal to 3, so far it moves from somewhere that is lower to higher. So from lower to higher, the rule is that it absorbs energy to do that. And we say it is excited. But to move from higher to lower, it emits or releases. And in that case, that's not excited. That's not an excited issue. So we just say it emits or releases energy. And then, so that's it. Emits releases energy. So, to be candid, we had made postulate 1, we had made postulate 2, we need to make postulate 3. All these are under Bohr. All these are rows of Bohr. Bohr making postulate 3 now. The third postulate of Bohr's model, is that angular momentum. Angular momentum values. Please take this class seriously. This is deep physics. I will not call it deep physics, but this is on building block. And don't say you don't need to know it. You need to know it. The third postulate of Bohr was that angular momentum values of the electron in an atom are quantized. That is, they are restricted to discrete values. And when we say angular momentum values, we're talking about L. They are represented as L. And I would love to okay. L values are h over 2 pi, but there is an n in front. And n, when we say they are quantized, means that n only has values of 1, 2, 3, 4, and goes on. So this is the formula for angular momentum values. So all the n's we've been talking about all this while, they are called, in this case of angular momentum, the n is called quantum number. So please take note of that. Let me make some statements before I call this class a wrap. It's getting long, but this class is very, very theoretical. You need to reread. You need to go into your jotter. Please be a student. Don't just be lazy. Don't just do things anyhow. Please take classes, go back, read, study, try to understand, memorize. I used to tell students, they say don't memorize. Memorize if need be. You need to just know some things because they are the building block for whatever you know else, or whatever else you would desire to know. So I go to the part that says Bohr model. It's also known as the Bohr-Rutherford model, since it was an extension. And one of the reasons why I believe that it was is because there was a point where I even explained that in Bohr's model, the nucleus is positively charged. Nucleus is positively charged, and but it's just that Bohr remodeled it such that we don't just have random orbits. We have organized orbits in form of energy levels. So, but many facts are similar in the two. The two agree that there is a nucleus that is positively charged and that there are orbits for the electrons that move around that nucleus. So that's good relationship. That's why people refer to it as Bohr-Rutherford model. It's an extension of Rutherford's planetary model, of Rutherford's planetary model. The great success of Bohr theory is that it gives a model for why atoms emit line spectra and accurately predicts for hydrogen the wavelength of the emitted light or the frequencies. So it predicts the wavelength and the frequencies accurately. First of all, gives a model that emits line spectra and predicts the wavelength or the frequency of the lines in the hydrogen spectrum. It offers some of these points can also be called the advantages of Bohr model. It offers an explanation for absorption spectra, photons of just the right wavelength and knock up an electron from one energy level to a higher one. Now, let me write it in red. This point two, this point we have just made, this explains why continuous spectrum passing through a gas will have dark lines at the same frequencies as emission line rather. So I want to quickly make the points here. Can reread them, understand them, memorize them. It ensures stability of atoms by stating that the ground state is the lowest state for an electron. So the ground state n equal to 1, and there is no other lower stage. So I don't need to add that comment. Just know that the ground state is the lowest state for an electron, n equal to 1. It accurately predicts the ionization energy of 13.6 electron volts for hydrogen. So that is the ionization energy. We'll discuss more on this concept in our next class. We'll go to the electron cloud model. But keep in mind that the ionization energy is 13.6 electron volts for hydrogen. And at some point, we'll talk about what ionization energy means. And please remind me to talk about that. But in our next class, we'll go to the electron cloud model. So I'll see you in the next class.